So this is joint work with so the yellow thing is on this. Okay. So this is a joint work with James Lee and Prasad Raghavendra. So I'll first talk about the context and the motivations for this work, and explain the main results at a high level. Later I'll make I'll give you the precise definitions and show you some of the proof ideas. Okay, but initially there won't be formal definitions, so don't be concerned about that. So the main result of this paper is our unconditional computational lower bounds for many classical combinatorial optimization problems like MaxCut and traveling salesman. And these lower bounds, they hold in a restricted but powerful model of computation that generalizes the best known algorithms that we have for these problems, which are based on linear and semi-definite programming relaxations. And in this the general model, our results are the first superpolynomial lower bounds for these problems. So this work is part of a research program that goes back to Yanakakis in the 80s, where it was a very remarkable paper. He was at the time motivated by what he wanted to do. He wanted to have a way of refuting several flawed P equals NP proofs, and he wanted to do it in a way that doesn't require checking each paper individually. So he wanted to rule out once and for all that algorithms based on these kind of methods can show that P is equal to NP. And so in this sense, this work achieves what Yanakakis wanted to do. There are also some so these kind of
so he was doing it for LP.
Right. I mean exactly. So and also he was doing it for symmetric. So he set up a framework for the general case, and he proved the lower bound for the symmetric case. The lower bound for the general LP case came quite a bit later. I'll talk about it. There's some connections to our results. So some of the questions that our results settles are they also came up in the optimization and convex geometry communities. So in particular, our results settled some open questions about spectrohedral lifts of polytopes and the positive semidefinite rank of matrices. But I'll not go into that today. So the general strategy for proving this lower bound is as follows. So what we'll do is we'll identify an optimal approximation algorithm in this general computational model, and in particular we will show that a concrete algorithm, this okay, somehow the pointer is not working. This sum of squares algorithm is an optimal approximation algorithm. It achieves approximation guarantees that are best possible among all polynomial time algorithms in this model for a wide range of problems, in particular for every constraint satisfaction problem, which includes MaxCut. Okay, the sum of squares algorithm, which is also known as the Lasser hierarchy, it's a very general, very powerful algorithm introduced by Shor, Perillo, and Lasser. And now, so with this kind of universality result in hand, the way you can derive lower bounds for the general model is by showing that it's just by showing counterexamples for this concrete sum of squares algorithm. And it turns out that there's a sequence of recent works and that provide such counterexamples for this algorithm, which are also called integrality gaps. And in the past years, we've developed quite a number of interesting techniques that allow us to show lower bounds for this particular algorithm. And now with this optimality result, we can lift all of those lower bounds to lower bounds for the general model. Okay, so let's talk about the kind of algorithms that our model is trying to capture. So for approximating NP-hard optimization problems, it turns out that the most powerful general approach to do that is using mathematical programming relaxations. And there are 3 flavors of these mathematical programming relaxations that are useful for approximating NP-hard problems. These 3 flavors are, linear, spectral, and semidefinite relaxations. So for a wide range of problems, the best known algorithms, they are based on linear programming relaxations. Then there are some problems like certifying edge expansion, where spectral techniques can do strictly better than linear programming techniques. And then there are problems where other kind of relaxations called semidefinite programming relaxations do strictly better than both linear and linear programming methods and spectral methods. And here MaxCut is a good example. So for MaxCut, it turns out that with semidefinite programming, you can get better approximations than with either linear or spectral techniques.
What is that figure it's talking about?
Which figure? This one? No, yeah, that's a good question. So I think that it shows the Zariski topology of the polynomials that define the boundary of the thing. So the orange thing is convex. I think the orange thing is what you care about. But somehow it's good to add this layer. So it looks more exotic.
Lambda, you understand.
Right. So lambda is an embedding of a graph that you get by combining the, I guess, first 2 interesting eigenvectors.
By the embedding of graph?
Yeah, you get it by looking at the first 2 interesting eigenvectors of the graph. So those give you the coordinates of the embedding. But yeah, the graph was chosen such that, not in the, okay. Okay, what is semidefinite programming? Okay, I'm sort of assuming that you have seen at some point maybe linear programs, and so spectral methods just refer to the idea that you compute eigenvalues or eigenvectors of a particular matrix associated with your problem, and so what is semidefinite programming? So a good way to think about semidefinite programming is that it's a way of combining in a systematic way linear programming and spectral techniques. And so that means that the picture is really more like this, where we have semidefinite programming as a unifying idea that captures both linear and spectral techniques. Also want to point out that there's a very intriguing connection of algorithms based on mathematical programming relaxations and NP hardness reductions. It turns out that in many cases, the failure of algorithms based on these methods can be translated to hardness reductions. And the most prominent case is, happens in the context of the Innie-Games conjecture, where there's a very general way of constructing hardness reductions based on the failure of these kind of algorithms. So in this sense, it's possible that these algorithms are not just the best known algorithms, but they could plausibly be the best polynomial time algorithms for these kind of problems. Okay, so that's the general class of algorithms that we are trying to capture in our model. And a priori, it's not clear that there should be a good way of formalizing, developing a formal computational model that captures these algorithms without capturing all of all polynomial time algorithms. But that was. But so Yannakakis showed that there is indeed a way of formalizing the intuitive notion of LP relaxations for a problem, and the formalization is is not too general. So it turns out that it has enough structure to allow for unconditional lower bounds, and only in 2012, Fiorini et al. Showed the first kind of unconditional lower bounds in Yannakakis' model, and after that work, there has been a sequence of results that extend Fiorini et al.'s work to the approximation setting and to other kind of problems. Another nice feature of Yannakakis' model is that it extends in a very natural way to SDP semidefinite programming relaxations. Unfortunately, the lower bound techniques, that work for the linear programming case, they break down. And it's not surprising because we know examples of problems where linear programming, where semidefinite programming is strictly stronger than linear programming. And so it means that lower bound techniques that work for semidefinite programs, they have to take into account this discrepancy. Okay, there's another. I also want to mention there's very interesting opportunities for to use Yannakakis' model to shed new light on interesting computational complexity conjectures about NP-hard optimization problems. So Yannakakis was interested in P versus NP, but there are many other conjectures about the complexity of optimization problems, and you could use Yannakakis' model to understand those conjectures. In particular, it would be interesting to understand if the Unigame conjecture is true in Yannakakis' model, or what's the best algorithm for planted clique in Yannakakis' model. So both of these questions, we actually don't know what the right answer should be, and Yannakakis' model could help understand those questions. Now let me describe Yannakakis' model at the example of MaxCut. It turns out that so MaxCut is just chosen for concreteness, but the description extends in a fairly straightforward way to pretty much any other optimization problem. So what is MaxCut? So MaxCut is in MaxCut you're given an n-vertex graph, and your goal is to find a bipartition that cuts as many edges as possible. And another way to think about MaxCut is that you want to maximize a particular quadratic polynomial over the n-dimensional hypercube. Okay, and this polynomial just counts the number of edges that are cut in the bipartition where the vertices with xi equal to 1 are on one side, and the vertices with xi equal to -1 are on the other side. Okay. And from this polynomial optimization viewpoint, it's also clear that another equivalent way to formulate MaxCut is that you want to maximize a particular affine linear function over the cut polytope, which is the convex hull of outer products of points on the hypercube. So you can see that evaluating this affine linear function on a point xx transpose where x is on the hypercube is the same as evaluating the quadratic polynomial at x. And now it looks like that we are sort of done, because this is already a linear programming formulation of MaxCut. We have a polytope, and we want to maximize a particular linear function over it. Okay, the issue with this way of obtaining a linear programming formulation is that the number of facets of the cut polytope is exponential. So if you want to describe it as an intersection of half spaces of linear inequalities, you need an exponential number of those. And so it means that there's no small direct LP formulation for this problem. However, this is just one particular way of trying to get an LP formulation for MaxCut. And what Yannakakis was trying to understand is sort of what's the way of describing all possible LP formulations for the problem. And he came up with a very nice geometric way of describing that. Yes.
By the way, there's another hardness result here, right? That a separating hyperplane is also for the cut.
I mean, it's hard. It's NP hard, right? I mean,
otherwise you could use ellipsoid.
yes. Okay, but here, I mean, notice that we are trying to prove things that are. Okay, much of this talk is about proving things unconditionally, as opposed to proving NP hardness results. Right? But yeah, it's true. So we. Yes. I mean, MaxCut is an NP hard problem. So yes. So nothing should be possible in polynomial time. But the challenge here is to prove that certain things are really not possible, as opposed to just proving reductions. Okay, and what Yannakakis proposed is that, his formulation of a general LP formulation of MaxCut, he says that there should be a polytope P, possibly in larger dimensions, that projects to the cut polytope. Okay, and if you had such a polytope where the the polytope upstairs is described by at most n to the d linear inequalities, then this would correspond to an LP formulation for max cut of size n to the d. Particularly, if d would be a constant, then independent of n, then this would be a polynomial. You could solve these. You could optimize over the polytope p in polynomial time. Okay, and maybe talk about this a bit more. So this process of lifting the cut polytope to some polytope that has a higher dimension, but that is described by fewer inequalities. Another way to think about it is that it's similar to allowing to introducing auxiliary variables to your linear program. Okay, and there are many examples, of in other computational models where allowing additional variables makes things more efficient than not allowing additional variables, and so here the question is, and something you want to talk about all possible ways of adding additional variables. Yes.
Why do you take only powers?
Say again? N to the d. So you talk about the n to the d? Yeah, just for notational simplicity. So I want to make. Yeah, d could be it's not necessarily integer. D could also be a function of n. So this is just to illustrate that this size has to grow with n at least. Right.
This would capture the cases when we have separation oracles, because sometimes.
Okay. Yes. So okay. Right. So separation oracles is always something that comes up here. So if you this the Anakakis model does not capture the general case of separation oracles. And the issue is that a separation oracle could do arbitrary polynomial time computations, and then there's really not much difference between asking. Can you solve the problem in P versus can you separate in P, right? Actually, that's the same. There's some some equivalence of optimization and separation. So, problem you can optimize in polynomial time if and only if you can separate in polynomial time. And so it means that if you sort of allow separation oracles, then you really didn't change the question. You just ask, is the problem in P?
Capture some specific separation oracle.
Yeah, exactly. So Yanakakis, yeah, exactly. So Yanakakis model captures a separation oracle where you just, where you have a list of constraints and you check each you have a polynomial list of constraints and you check all of them. And the more general model of SDP formulations, you can also think of it as relying on other, allowing more general separation oracles where you're allowed to do sort of eigenvalue computation in your separation oracle. That's right.
There are some examples where the separation oracle comes from finding shortest path in a graph.
Right. So those are so shortest path is an example where you can find small LPs also. And so I think the only sort of classical combinatorial optimization problem that you can solve in polynomial time, where you don't have a small linear program, is matching, matching in general graphs. So that's, but notice that.
Solving linear equations, maybe, right?
Yeah, I mean linear equations over over finite field, right? In some sense, yeah, that's a little bit. I mean, the separation oracle for maximum matching does something a little bit similar to that because there's some odd-even business going on. Yeah, that's true. So yeah, it doesn't capture all polynomial time algorithms, unfortunately.
If you're interested in approximation algorithms, do you really want the projection to be equal to the cut, or?
Right. So this is that's a good question. So this is the formulation for that it corresponds to solving the problem exactly. It turns out that if you want to talk about approximation, then this viewpoint in terms of polytopes, it becomes very cumbersome. We will later see an equivalent, more useful, way of talking about these things that where it's very natural to talk about approximation. So in terms of polytopes, it's a bit tricky to talk about approximation because how should clearly the projection should not be the same, but somehow it should preserve some kind of the shape of the original of the cut polytope, and it's just a bit awkward to describe in what precise sense should it preserve the cut polytope. So this means that if you had this kind of LP formulation, it would allow you to solve max cut exactly in time n to the order d. Okay, and so there are many examples where you have downstairs a polytope with exponential number of facets, but it's nevertheless the projection of a polytope with a polynomial number of facets. Okay, and so these are a list of examples, and I will show you in a bit a concrete one. So the question that we raise now, that we want to address, is can we prove size lower bounds on the for LP formulations of max cut? And we expect these things to be we very strongly believe that these things are true because they're implied by things like by the circuit version of P not equal to NP. So the only question is, can we prove it? So here's a very short example of a polytope where you can have exponential savings by projecting. So consider the unit ball of the L1 norm. So all vectors where the sum of the absolute values of the coordinates is at most 1. It's not hard to see that you need 2 to the n linear inequalities to describe this polytope. Basically, for every possible way of replacing the absolute value sign by plus or minus 1, you get a new linear inequality that you need to describe the set. But at the same time, this polytope is a projection of a polytope that has n more variables, but requires only order n linear inequalities to describe. Okay, and so you add these additional y sub I variables, and y sub I, what it tries to do is it tries to capture the absolute value of xi. Okay, so here you introduce a variable that's supposed to capture the absolute value of xi, and now suddenly everything becomes very easy to describe. And in Yanakakis' model, you want to consider all possible ways of introducing additional variables. Okay, and in 2012, Fiorini et al. Showed that indeed you can't have small LP formulations for max cut, so D has to be roughly n if you want into the D size LP formulation for max cut. And this is about solving the problem exactly. You can extend Yanakakis' model so that it allows you to talk about approximating max cut, and what you can show in that approximation model is that if you want to have a LP relaxation for max cut that achieves an approximation ratio of better than 1/2, you need superpolynomial size LPs. Okay. And at the same time, you can achieve approximation ratios of 1/2 with very small LPs.
This separates LPs from SDPs.
Exactly. So this sort of gives a very good understanding of LP algorithms for max cut, but the issue is that they're actually very simple SDP algorithms that achieve approximation ratios of better than 1/2. So this means that LP algorithms are not really the right model to study max cut, and instead we want to consider SDP formulations for max cut, and Yanakakis' model, this geometric viewpoint, it's very easy to extend to SDP formulations. So the only thing that you have to change is instead of asking for a polytope that projects to the cut polytope, you ask for a spectrohedron to project to the cut polytope. And a spectrohedron is a convex set that is described as the intersection of affine linear subspace and the cone of positive semidefinite matrices. Okay. And the size corresponds just to the dimension of the matrices. Okay, so then the picture becomes something like that. And in this work we show the first lower bounds for superpolynomial lower bounds for SDP formulations. In particular, we show that max cut requires exponentially large STP formulations. Again, one can extend it to the approximation setting, and here you get that approximating max cut within 0.99 requires superpolynomial size STPs. And in general, you can match. So the approximation ratio that you can have here is, for an arbitrary CSPs, whatever the best known NP hardness result gives you. So here we can match
With
the,
current techniques.
Yes, with current techniques. Yes.
I mean, somebody else could prove it in some completely different way that it wouldn't match.
You mean you could prove NP hardness in a different way? Yes, that's true.
Because we don't have optimal NP.
That's right. Yes. Yeah. Match the current. Yeah. What I mean is you can match the current NP hardness results for CSPs. As I said before, we also identify the optimal approximation algorithm in this case. And so what it means is that if you look at the best approximation ratio achieved by n to the d size STP for max cut, this is no better than the approximation ratio achieved by the sum of squares algorithm of comparable size. Okay, so the sum of squares is a concrete STP algorithm, and if you look at the corresponding size version of sum of squares, then you get at least an approximation ratio. Okay. Now, so that's the description of the results. Now let me. Now I want to explain some of the proof ideas. So it turns out that this geometric viewpoint of LP and STP formulation in terms of polyhedra and spectrohedra, it's very nice, very elegant way of describe Yannakakis' model, but it's not so useful for proving things about it. And it turns out that there is an alternative way of thinking about Yannakakis' model, which is very useful for proving lower bounds. And so this. So the starting point of this alternative viewpoint is following simple observation. So observation is that if you have some optimization problem like max cut, and you have some approximation algorithm for this problem, then which achieves this approximation algorithm achieves, and if the approximation algorithm achieves an approximation ratio of alpha, it implies that the algorithm can certify upper bounds on the objective function. And the upper bounds are not too far from the true optimal value of the objective function. Okay, so in max cut, you try to optimize this quadratic function over the hypercube, and if I just give you this function, you don't know what's the largest value it takes, and if you have an approximation algorithm, what it allows you to certify that some upper bound on the maximum value of this objective function, and this upper bound is promised to not be too far away from the true optimum value. Okay, and it turns out that it's very so STP and LP algorithms, they have very nice characterizations in terms of the kind of certificates that they use. Okay, so for example, this degree D sum of squares algorithm that I've mentioned, which is an example of an n to the d size STP. Here are the kind of certificates that it can use. So it can certify that a function f is non-negative if and only if this function is equal to a sum of squares of functions that have degree at most d. Okay, and notice that. So here I'm talking about functions on the hypercube. And so this equality is, in particular, means that these two functions should be equal as a function on the hypercube. And so this captures precisely the kind of certificates that the algorithm can use. And with this, now if you have this definition, and together with this connection between approximating and certifying, you can ask what's the best approximation that sum of squares can achieve. Okay, so you can just need to ask, what's the smallest d, such that I can certify these kind of bounds using in this way. As an example, so these kind of certificates, they they sound like, they're very simple. It's almost too simple to be useful. But it turns out that these kind of certificates really capture the best known algorithms for a wide range of problems. So in particular, so why are these funny symbols there? Does someone? Okay, so that's good. So in particular, this is the way that that degree 1 sum of squares captures the Grimmins-Williamson approximation algorithm for maxcut. So the Grimmins-Williamson algorithm is the best known approximation algorithm for maxcut, and it achieves a 0.878 approximation for the problem. So here's a way to capture that. So it turns out that for every graph G, if you look at the function optimum value of G, which is a constant, minus 0.878 times the objective function for G. So now you have a function on the hypercube, and then this function is equal to a sum of squares of linear functions. Okay, and this is true. For every graph, you can find linear functions such that this is true. And this is an equivalent way of saying that degree 1 sum of squares captures, achieves a 0.878 approximation for maxcut. Okay, sorry to expose you, to my handwriting. I don't want to prove this; it's a bit too technical. But let me prove you a slightly weaker result. Let me show you how degree 1 sum of squares captures spectral relaxations. So what's the spectral relaxation? So recall that our the objective function for maxcut is a quadratic form. Often, this matrix is called the Laplacian, and so one way to upper bound this quadratic form is to use, you can upper bound in terms of the largest eigenvalue of the quadratic form. Okay, and then you get an upper bound of lambda max times n. So n is just the norm of the vectors that we talk about here. And here is a way of capturing this upper bound in terms of degree 1 sum of squares. So if you look at the function that you're trying to certify to be non-negative, then again this is a quadratic form, and you notice that the matrix here is positive semidefinite, so you can take square roots, and now you see that is equal to this norm, and you see that this here is a sum of squares of functions that have degree 1 in x. Okay. Okay. So in this sense, degree 1 sum of squares captures spectral relaxations. Right. So there's a connection to of sum of squares to the Nier-Games conjecture. It turns out that sum of squares is the best candidate at the time to refute the Nier-Games conjecture. And in particular, if you wanted to refute the Nier-Games conjecture, all you have to prove is the following. You have to prove that there exists some constant d, such as for every graph, if you look at this function, which is slightly less, so this constant is a bit larger than this one. If you look at this function, it's a sum of squares of functions of degree at most d. So if you can prove that, it would refute the Nier-Games conjecture. And so here we saw, degree 1 achieves some guarantees, and here we're asking whether some other degree works better. So in general you can ask, does it help to choose a larger degree? And like the generic answer is yes, it does help. In particular, for every function that is non-negative, you can find a function g on the hypercube such that f is equal to g times such that f is equal to g squared. Just interpolate the square root of f over the hypercube, and this function g has degree at most n. So it means that if you allow functions of degree n in your decomposition, then you can certify that everything that is non-negative, you can certify that it's non-negative. And unfortunately, the size, this would correspond to a SDP of size 2 to the n. So it's not interesting from a computational point of view. Okay. So here, okay, I'm talking about. So I'm claiming that I'm talking about SDP relaxations, but there's sort of this persistent rumor that SDPs are about assigning vectors to vertices of your graph. I'm not sure. If you haven't heard that rumor, then you don't have to worry. So just if you're concerned about where are the vectors, here are where the let me show you where the vectors are. So in some sense, the reasons why there are no vectors is because I'm talking here about the problem of certifying that there's no good max cut. So the vectors come in as a way of in some sense, if you fail to certify that there's no good max cut. So if you have a solution, then you get this vector solution. And okay, so let's see how we get the vectors from the failure of these certificates. So suppose that there's no that we can't have we don't have a degree D certificate for sorry, that this should be at most F. Sorry about that. At most C. So suppose you don't have a certificate that the maximum value is at most C. So then what this means is that if you look at the function, okay, somehow all the signs are off here. If you look at the function C minus F sub G, this is a function that is not in this set. Okay, that is not, so this set here is the cone that consists of all sums of squares of functions of degree at most D. So this is so if you think about it geometrically, it's just a cone, like an ice cream cone. And if the function C minus F sub G is not in that set, what it means is that there's a separating hyperplane that separates the function C minus F sub G and from the cone. And this separating hyperplane corresponds to a function D on the real value function D on the hypercube. And here are the properties of this function. So so this property means that every square of a low degree function is on is on one side of the hyperplane. And this property means that our function C minus F sub G is on the other side of the hyperplane. And this here is just some normalization. Okay, so these are three properties that the hyperplane satisfies. And now, if you look at the following matrix, that you get by sort of summing up d of x times the outer product of x, then it turns out that this is you can show that this matrix is positive semi-definite, and it has the property that the diagonal entries are 1. Actually, maybe let's see why the diagonal entries are 1. So the way to see it is that every diagonal entry here is 1, and the sum of these values is equal to 1. This is the normalization. So that implies that the diagonal entries of M are 1. And it turns out that this property also implies that this matrix is positive semi-definite. And that means that there are unit vectors v sub I for every I, such that the entry Mij of the matrix is equal to the inner product of Vi and Vj. Okay. So this is basically you get the vectors by duality, and somehow doing this in some sense doing this moment construction. So I
should it also give the higher moments?
Yes, it should also give you the higher moments. So I just showed you how to get the degree 2 moments.
Oh, I see.
Yeah. So if you would here sum up outer products of x tensor D, then you would get higher moments, and they would still be PSD. So I was showing you this because there was this intermediate object D, which was just a separating hyperplane. But actually, this intermediate object D is it's interesting in its own right. So one way to think about D is that it satisfies properties that would be satisfied by a probability distribution over max cut solutions, such that the expected value under this probability distribution is bigger than C. Okay, so if you think of having a probability distribution over solutions, max cut solutions with expected value bigger than C, then you would assign a probability to every point x, and you can think of d of x as this kind of a probability, and then this here would just say that the expected value under the distribution of g squared is non-negative, which is true because g squared is a non-negative function. The expected value of 1 is 1, and the expected value of your objective function should be bigger than C. And then this object here would be the second moment matrix under the probability distribution. Okay, and this intermediate object, if it just satisfies these three conditions, we call it a pseudo distribution, and this is actually a useful way to think about LP and STP relaxations in general. So this kind of object you can always get if you have LP or STP relaxation. Okay. So now we saw that we can think about this degree D sum of squares algorithm as in terms of the kind of certificates that it uses. Now, what are ways of now what we would like to do is we would like to understand the for a general STP algorithm, how can we characterize the certificates that it uses? It turns out that if you have a general STP algorithm, you can generate all the certificates that it can use by a single positive PSD matrix valued function Q. Okay, so you have a function Q that maps every point on the hypercube to some PSD matrix. And this single function, it characterizes all the certificates that the algorithm can use. Okay, and the way it generates the certificates is in this way. So don't read it now. So let me first show you an example. So it turns out that the degree D sum of squares. So if you look at this algorithm, the way you would get it in this way would be to choose Q to be the outer product of X tensor D. Okay, and maybe let me just show you how to get the sum of square certificates in this way. So if you want to generate this function, then you can think of it as if Gi has degree D, you can think of it as in this way. You have some vector capital G sub I of dimension n to the D, inner product with X tensor D, and you square this inner product. And now this is equal to the sum over I of Gi transpose times X tensor D transpose. And so this would be so you could choose this to be P. And this was our choice of Q. Okay. And so in general, the way you generate certificates from this single PSD matrix valued function is by taking a PSD matrix P and you use this PSD matrix P to flatten the function Q to a real valued function. Okay, and you go over all possible matrices, PSD matrices P, and as you go over all possible PSD matrices P, you generate all the certificates that the algorithm can use. Okay, and it turns out that so here's another observation. So if you have a general STP algorithm Q, so if I just tell you, here's the function Q that the algorithm uses, then one way to test whether it's captured by degree D sum of squares is by testing whether the square root of Q has degree at most D. So so here degree is as a function of X. So the square root of Q, it's some other matrix valued function, and you just ask, are the entries of this matrix valued function, are those degree, are those polynomials with degree at most D? So why is that? Because the kind of certificates that the algorithm can use, you can also express it in this way. And now you see that the kind of certificates that the algorithm can use, they are sums of squares of of things involving the function square root of Q. And so if square root of Q has small degree, then these guys here are sums of squares of polynomials with low degree. Okay, and remember, so this is useful because remember our goal is to show that a general STP algorithm can be simulated by sum of squares. Okay, so it means that if you wanted to prove that okay. So let me say this first. So if you wanted to prove that the general STP algorithms can be simulated by sum of squares, one way to do that is to show that somehow for every PSD matrix valued function Q, I can approximate it by another function that satisfies this condition. Okay, so somehow this condition is a good way to identify whether your STP algorithm is captured by sum of squares. Yes.
Degree is the NGYS maximum of the NG.
Yes, the maximum NGYS degree. Right.
And the degree of the function is just the
Yeah, the usual degree of a function on the hypercube. Exactly. So here everything so all functions are functions on the hypercube, and so we measure degree as we're used to. So let me describe briefly where this function q comes up. Okay, so basically justifying this claim that somehow this is these kind of things really correspond to general STPs. Okay, so suppose that we have some spectrahedron. Okay, so that defines our STP. And now, what does it mean that it's a relaxation of max cut? So one thing that it means is that for every true solution x for our max cut problem, we should have a solution z sub x in the spectrahedron. Okay, so just think about that if you try to get a LP relaxation for max cut, that's something that we have to do for every actual solution. Your relaxation should have a corresponding solution. So those are the c sub x's, and there should also be a way of taking of simulating the objective function that you care about in terms of linear functions on sort of in some kind of inner products in this way. So there should be cost functions y sub g such that the inner product of y sub g and c sub x is equal to the objective value of x for the graph G. And now the way we can choose q is we want to define now a function q that captures this STP relaxation from x cut. And the way we do it is we define q of x to be the slack of this constraint at the point z sub x. Okay, so we have this constraint that defines the spectrahedron, and q of x will just be the slack of this constraint when we look at the solution c sub x. Okay. Now the reason why this q generates all the certificates that the LP relaxation, STP relaxation has access to is basically due to duality. So duality says that this constraint, the optimum value of the function y sub g over the spectrahedron is at most c, if and only if it's possible to generate this inequality from the constraints that define the spectrahedron. And it turns out that the way you generate these constraints is by taking you look at the constraint that defines your spectrahedron, and you just look at the trace of this look at the trace of some PSD matrix times the constraint. So this this is the analog of taking non-negative combinations of your constraints. Okay, instead of taking non-negative combinations, you take the trace of some PSD matrix with your constraint. Okay, so in the linear programming case, you would take non-negative combinations of your constraints, and that's the analog in the spectrahedral case. And now you see that the way we set things up is that this is our function c minus f sub g, and we chose q in such a way that that we have this identity. So this is why every STP relaxation for max cut is captured by some function q of x. Okay, so now what we want to show is that if you have such an arbitrary function q, you can simulate it with degree d sum of squares. And so what we would like to do is we would like to show that for every n to the d size STP algorithm q, where q just is this matrix, this function, you can approximate, you can find some other function q prime. Sorry. Okay, yeah. Let me first say it like this. So you would like to approximate it by some function that satisfies this. Okay, and the key ingredient of our proof is to prove some weaker version of this first. And the weaker version is that we want to approximate q by some function q prime, such that the degree of the square root of q prime is logarithmically large. Okay, so if if you could have a bound of d here, then that would clearly be captured by degree d sum of squares, and it turns out that this logarithmic bound is enough to makes huge progress to this goal. And there's another argument to sort of reduce this logarithmic to get rid of the logarithmic factor. Okay, so this is some goal that we have, and now one important step is to sort of clarify the notion of approximation that we need. So we want that q and q prime should be similar. It turns out that you can. There's a very V condition that is sufficient. We just want that for every low degree matrix valued function f, the correlation of f and q should be similar to the correlation of f and q prime. And the nice thing is that it's enough to choose to find q prime sort of that depends on f. Okay. So what we now want to show is that for every n to the d size STP algorithm q, and for every low degree matrix function f, we want to show that there exists a low degree STP algorithm q prime that correlates such that the correlation of f and q is the same as the correlation of f and q prime. Okay. And so this is the key ingredient of the proof. And let me show you that that proof. So first of all, like this kind of theorem, it falls into a general framework of theorems. There are many versions of that, where you have some object, and you want to approximate the object with respect to a family of test functions. Okay, and here, so these are our test function, and the general phenomenon is that if you want to have this kind of approximation, then the approximator need not be more complex than the tests. Okay, so this is the general phenomenon, and this would imply. So in this setting, it would indicate that that the approximator q prime can be chosen such that the degree of q prime is small. Okay, but we really want the degree of the square root of q prime to be small, and this is a key difference, because if you have a function on the hypercube and you take its square root, typically the degree will be much larger than before. Okay, so what's the challenge here is to have a way of bounding the degree of a square root of a function. Okay, and so here is the approach. So in principle, what we would like to do is we would like to find. So we have this goal. We have this. We have q, and we have a test f, and we want to find q prime that behaves similar with respect to the test f, and in something, and we want q prime to choose q prime in such a way that the degree of the square root of q prime is as small as possible. Okay, so somehow the degree of the square root of q prime is a very it's hard to understand, and so what we do is, instead of trying to control the degree of the square root of q prime directly, we will just ask for we will ask for the simplest q prime in a different with respect to a different measure. And the way we measure the simplicity of our approximator q prime is in terms of an appropriate notion of entropy. Okay, so what we'll ask for is we want to choose q prime such that it approximates q with respect to the test f, and it maximizes an appropriate notion of entropy. And the appropriate notion of entropy turns out to be the von Neumann entropy, which is like a quantum analog of the classical Shannon entropy. And now so if you're at this point, you are in pretty good shape, because you now just try to find matrix valued function q prime that passes the test f and has maximum entropy. So now you have a nice optimization problem, and you can ask about properties that the maximum entropy solution satisfies. And it turns out that the maximum entropy solution to this problem, it has actually a closed form, And the form is you can choose Q prime to be the matrix exponential of t times f of x. Okay, and where t is where t is a function of where t turns out to be just the entropy deficit of Q, and it turns out that t you can bound t because Q was a small was a small SDP algorithm, and so there's it turns out that sort of this process of finding a matrix function that has so this kind of optimization process, it also comes up in matrix multiplicative in an algorithm for solving STPs, which is called matrix multiplicative weight update. Okay, so why does this make progress? So here's why it makes progress, and this is sort of the end of the talk. So recall that we wanted to bound the degree of the square root of Q prime. Okay, so this tells us that we can choose Q prime in this way. Now the square root of Q prime we can we just get by dividing the exponent by 2, and now we can if you look at the Taylor expansion of this, we can see that the degree is controlled by t and by the degree of f. Okay, but our assumption was that the degree of f was small, and so that means and also t was small, and this means that the degree of this here is indeed small.
This is still not as small as you want.
Right. It's logarithmic, and there's an additional argument to show that once it's smaller than once it's reasonably small, you can make it very small. So there's some in some sense this is like a bootstrapping argument where you want to show that it's that it's not terribly bad, and then there's an amplification step where you can say that once it's reasonably good, it's actually very good.
So t is a real number.
T is a number, right?
So Q only depends on Q via this real number t.
Say again?
So in the definition of Q prime, it only depends on Q via this real number t.
That's right. Yes. So okay. So there's right. So this looks a bit suspicious, right? Because we want to approximate f with respect to this thing. So but notice that f is really just a linear function, and in some sense Q prime is the the way of minimizing this linear function. Over all things that are similar to Q.
Here you stop at t just because.
So in the Taylor expansion, right, exactly. So it turns out that t, the magnitude of t, essentially coincides with the point where you can truncate. Right. And so this is the proof of this key ingredient. So let me sum up. So what we saw is a way of interpreting a general small SDP algorithm as in some sense a quantum state, and the quantum state has the way you see that it corresponds to a small SDP is in terms of its entropy, and then we were able to approximate this general SDP by a low degree SDP using some kind of a maximum entropy optimization procedure, which is also related to sort of some kind of learning algorithms. And here are some open questions. So the open question I want to focus on is this one. So it turns out that so from what I showed you, actually nothing was really specific to maxcut. Okay, so we didn't really use any properties of the hypercube. It turns out that sort of in this second step where you want to reduce the degree from log n to something really small, that's a place where you use properties of the hypercube. And but in general, you would like to do a similar kind of arguments for other problems, in particular for traveling salesmen. So here, for example, for Turing salesman, we don't know how to show that a 0.999 approximation of Turing salesman is. We don't know how to show lower bounds for that.
It's always with a travel inequality.
Metric version. Yes. Exactly. And then there are two quantitative questions. So just sometimes we don't get the kind of quantitative bounds that you would expect, and in terms of the size. And there's a recent news that one of these questions was solved by Raghavendra, Mekka, and Kothari. Thank you very much.